Hello, this is John Miares, and in this lesson, we're going to look at how to solve trigonometric equations, which are essentially equations involving trigonometric functions or expressions. This is the next logical step in your study of trigonometric functions. And if you think about it, it follows the same pattern of how you've learned to solve other types of algebraic equations in previous courses. First, you worked with intermixing variables with numbers, learned the basics of the order of operations, then solved simple equations. Then you worked your way up to quadratic expressions, distributing, foiling, etc., and then you learned how to solve quadratic equations. Then you moved along to higher degree polynomials and their properties and learned how to solve equations involving them using synthetic division or the rational root test, factoring by grouping. Then you learned about radicals and radical equations, exponential functions and exponential equations, logarithms and logarithmic equations. Now that we've seen the ins and outs of trigonometric functions, it's time to look at trigonometric equations. Before we can begin to solve trigonometric equations, we need to ask ourselves the following question. Is calculating the square root of 4 the same as finding the solutions to the equation x squared equals 4? If you recall, we discussed this idea a bit when we were first looking at inverse functions earlier in this unit. If you were asked the question directly, what is the square root of 4? You're going to tell me that the answer is 2. Some of you might also say, well, what about negative 2? And while negative 2 is a square root of the number 4, it is not the square root of 4. When we were forced to define the square root function as a function, we restricted the range to consist of only positive numbers so that this graph could pass the vertical line test and satisfy the definition of a function, where each x plugged into the function can only generate one y value. For the square root of 4, we're going to just say that it is 2 and ignore the negative square root. So how many values does the expression square root of 4 have? 1. Simply put, when asked what is the square root of 4, it's going to be just 2. Now let's look at this from the other side. How many solutions does the equation x squared equal 4 have? Let's look at the graph of this as well. This is the graph of y equals x squared. And here I'm going to draw a horizontal line through the parabola at y equals 4. The golden rule of graphing, which I've touted many times before, says that every point on the graph of an equation is a solution to the equation. So every point on the parabola is a solution to the equation y equals x squared, whether it's 0 squared equals 0, 1 squared is 1, 2 squared is 4, and so on. If I were to look at where the two graphs cross each other, that will represent the place where the two equations have solutions in common. Where y equals x squared crosses y equals 4, that will be where x squared equals 4. What you should notice here is that this line crosses the parabola twice at the point negative 2, 4 and positive 2, 4. This tells me that the equation has two solutions, which will be when x equals negative 2 and x equals positive 2. This is why the rule when you've solved these quadratic equations out has been that when you introduce a square root sign, you need to introduce the plus or minus sign in your solutions as well. More specifically, when we try solving the equation x squared equals 4 and take the square root of both sides, technically what we have in our equation is absolute value of x equals 2, which will give you x equals positive 2 or x equals negative 2 as your final answer. Let's extend this idea to trigonometry. If I were to ask you if computing the inverse cosine of 1/2 was the same thing as solving the equation cosine of x equals 1/2, what might you tell me? Well, this is a recording, so I can't hear you. But let's see if we can approach this from the same perspective as we did with the square root function. Starting more simply, how many values does the expression inverse cosine of 1/2 have? I would hope that you would tell me 1, because just like with the square root graph, the inverse cosine graph has a very restricted range. We said that if you're going to take the inverse cosine of a positive number, the answer you will get has to be some angle between 0 and pi radians, or between 0 and 180 degrees. Here, you're going to see that the inverse cosine of 1/2 is pi over 3 radians, or 60 degrees. Now let's ask, how many solutions does the equation cosine x equals 1/2 have? If I look at this from the same perspective as we did the problem x squared equals 4, we could try to graph the function y equals cosine of x and draw a horizontal line through it at y equals 1/2. Although I haven't labeled the points explicitly here, what you should see is that this horizontal line is going to intersect the cosine graph in several places, including pi over 3, 5 pi over 3, then back here at negative pi over 3, negative 5 pi over 3, and if we were to extend our cosine wave further in both directions, we'd see a lot more intersection points with the cosine wave along with this line y equals 1/2. Long story short, how many solutions does the equation cosine x equal 1/2 have? A lot. The purpose of this lesson is to look at problems like this and come up with strategies for how we can explicitly state the solutions to the equation cosine x equals 1/2, knowing it could possibly have an infinite number of solutions. There are 3 ways we can look at solving equations like cosine x equals 1/2. The first thing we can do is look at it from the reference angle perspective by using the inverse cosine. In this case, we know the inverse cosine of 1/2 is 60 degrees, so 60 degrees is definitely going to be one of the solutions. The next step is to expand this to look at all of what we would refer to as the primary solutions, which would include all possible solutions to the equation between 0 and 2 pi, or 0 and 360 degrees. Essentially, one full revolution of our unit circle. We could look on the graph and see that it does look like between 0 radians and 2 pi radians, we have 2 intersection points, one at pi over 3 and one at 5 pi over 3. These two would be considered the primary solutions. Those are the 2 angles between 0 and 2 pi where the cosine of the angle will equal 1/2. The third way to look at this is to consider all possible solutions from negative infinity to positive infinity. We call these the general solutions, and there's going to be a pattern to these which isn't completely obvious because I haven't extended the graph here that far in both directions. But when you think about it, if the cosine of x is 1/2 at pi over 3 radians, or 60 degrees, then the cosine of x must also equal 1/2 at any angle coterminal with 60 degrees, or pi over 3 radians. The same can be said with any angle coterminal with 5 pi over 3 radians or 300 degrees. Those coterminal angles create the same reference triangle. So in all of those cases, you're going to have adjacent over hypotenuse equal 1/2. The challenge will be to figure out the best way to express all of those solutions because in theory, there are an infinite number of angles that will be coterminal with our two primary solutions. As we move forward, for the most part, we want to find general solutions. But in order to do that, we first have to find the reference angle and then the primary solutions before we can even begin to think about the general solutions. Let's say we want to find the primary solutions to the equation cosine of x equals 1/2, but we don't want to do it graphically looking where the cosine wave will intersect that horizontal line. Here's what we're going to want to do. Our first step is going to be to take the inverse cosine of 1/2 to get the reference angle solution. We know from our previous experiences, and hopefully through our work with mad minutes, that the inverse cosine of 1/2 will be 60 degrees or pi over 3 radians. This is our reference angle solution. The next step will be to look at the quadrants where the equation should have solutions. We want to know where the cosine of x equals 1/2. 1/2 is a positive number, so we can use our all skiers take chances pattern to determine that the cosine of x will be positive in quadrants 1 and 4. So now we're going to draw a graph, not of a cosine wave, but of two reference triangles, one in quadrant 1, one in quadrant 4, that will represent the primary solutions to this equation. So I'll start by setting up my axes. I need to draw two angles in standard position, one in quadrant 1 and one in quadrant 4, such that the cosine of those angles, when I put in the reference triangle, will equal 1/2. We know the reference angle is 60 degrees, so I'm going to measure 60 degrees off the x-axis in quadrant 1 and 60 degrees off the x-axis in quadrant 4. In quadrant 1, that angle will just be 60 degrees or pi over 3 radians. In quadrant 4, that's going to be 300 degrees because you're taking 360 minus 60, or looking at that in radians, you get 5 pi over 3. What we can say now is that the two primary solutions for this equation, those that are found by going around the circle once, are going to be at 60 degrees or pi over 3 radians, or at 300 degrees or 5 pi over 3 radians. Our next step is to expand on our primary solutions to get the general solutions. As I mentioned before, the general solutions are all the ones that are coterminal with the primary solutions. So if the primary solutions are 60 and 300 degrees, or equivalently pi over 3 and 5 pi over 3 radians, we would say that the general solutions are going to represent every angle that is coterminal with these two. However, there's got to be a way, perhaps some shorthand notation that we can use either so that we don't have to list all of the possible solutions or write this out in words. Any two angles that are coterminal with each other, recall, are going to be differing by multiples of 360 degrees. So if we were to list them all off, they essentially form an arithmetic sequence. Ooh, I bet you weren't expecting to hear those words again until the final exam. They form an arithmetic sequence where your first number is either 60 degrees or 300 degrees, and your common difference is 360 degrees. The notation we will use is going to look something like this. What we're going to say is x equals 60 degrees plus 360k, or 300 degrees plus 360k. And then we have this funky notation over here with the k and this bent out e and this double barred z. This notation is a mathematical shorthand that says k is an integer. Now remember, integers can be positive or negative whole numbers. They could be 0, 1, 2, 3, 4, and so on, but they could be -1, -2, -3, -4, so on. Infinitely in both directions, we're going to get lots of possible answers that we could get for x. So whatever integer value you plug in for k into this formula, either 60 plus 360k or 300 plus 360k, will give you a solution to this equation. The radian approach is similar, except instead of saying we're going to add multiples of 360 degrees to our primary solutions, we're going to add integer multiples of 2 pi radians to pi over 3 and 5 pi over 3, our primary radian solutions. Before we go on to the next slide, I just want to summarize the process that we used here. First, we took the inverse cosine of 1/2 to get the reference angle, 60 degrees or pi over 3 radians. Knowing that 1/2 is a positive number, we then had to figure out what quadrants this would have solutions in. Cosine of theta is positive in quadrants 1 and 4, so we needed to figure out what it meant to be a 60-degree angle in quadrant 1 and a 60-degree angle in quadrant 4. We drew the reference triangles in these quadrants and figured out that their measures were going to be 60 degrees or 300 degrees. Those are the primary solutions. The general solutions were then just going to be anything coterminal with those. And to find coterminal angles, you just add or subtract multiples of 360 or multiples of 2 pi radians to your primary solutions. Since integers can be positive or negative, I don't need to use the plus or minus sign in front of the 360k or in front of the 2 pi k. Using a plus sign is fine, but it is important to know that k has to be an integer, which is what this k and the bent out e and the double barred z are going to tell you, because k cannot be a fraction. I cannot have fractional multiples of 360 degrees. That's not going to get me the coterminal angles we're looking for. Let's try another one here. Suppose we're interested in finding the primary solutions for the equation sine of x equals -1/2. My recommendation here is to first take the inverse sine of +1/2 rather than -1/2, because by using +1/2, we'll be able to know the appropriate acute reference angle solution, because taking the inverse sine of any positive number will always get you the angle back in quadrant 1. When you take inverse sine or inverse cosine or inverse tangent of a negative value, the solution quadrants, remember, are not going to be consistent. But if we take the inverse sine of 1/2, we're just going to get 30 degrees or pi over 6 radians. This is going to be our reference angle solution. Next, we want to see what quadrants the equation is going to have solutions in. Since we want to solve for the sine of x equals -1/2, we have to ask ourselves, in which quadrants would we expect to see values of the sine function come out negative? Well, the sine of x is positive in quadrants 1 and 2, so the sine of x has to be negative in quadrants 3 and 4. Now let's construct two reference triangles, one in quadrant 3 and one in quadrant 4, that will get us the primary solutions for this equation. So we'll start with a set of axes and draw two terminal sides here, one in quadrant 3, one in quadrant 4. Then we'll drop a perpendicular segment back to the nearest x-axis. The reference angle is 30 degrees. So now we have to ask ourselves, what does it mean to be a 30-degree reference angle in quadrant 3 or a 30-degree reference angle in quadrant 4? In quadrant 3, we'll add 30 degrees to 180 degrees to get 210 degrees. Or equivalently, we could add pi over 6 radians to pi radians to get 7 pi over 6 radians as our first primary solution. In quadrant 4, we'll subtract 30 degrees from 360 to get 330 degrees, or in radians, we would subtract pi over 6 from 2 pi to get 11 pi over 6 radians. From here, the general solutions will represent all of the ones coterminal with the primary solutions. Here are our primary solutions again. These are the ones that fall within one revolution of the unit circle, either 210 degrees or 330 degrees. In radians, 7 pi over 6 and 11 pi over 6. The general solutions can be written just like we did in the previous example. So you have 210 degrees plus 360k and 330 degrees plus 360k, where k is an integer. The radian equivalent of this will be that x can equal 7 pi over 6 plus 2 pi k radians, or 11 pi over 6 plus 2 pi k radians, where k is an integer. And this will be our final answer. Here's one you can try on your own. You want to try to find the primary solutions, then eventually the general solutions to the equation tangent of x equals -1. The step I want to remind you of first is to take the inverse tangent of +1 and not -1, so you can get an acute reference angle whose measure is going to be something between 0 and 90 degrees or 0 and pi over 2 radians. Then we'll look more closely at which quadrants will have solutions in based on the all skiers take chances pattern, which has the function being positive in quadrant 1 and quadrant 3, or being negative in quadrants 2 and 4. Let's pause this video for a few minutes to see if you can do this one on your own. All right, so the inverse tangent of 1 is going to be 45 degrees or pi over 4 radians. As I said earlier, tangent is positive in quadrants 1 and 3, but we're trying to solve where tangent of x equals -1. Tangent of x is negative in quadrants 2 and 4. Next, let's construct the reference triangles in quadrants 2 and 4 to see what the primary solutions are going to be. When I do that, we'll have something like this, where the terminal sides of the angles are in quadrants 2 and 4, measuring 45 degrees off the nearest x-axis. That will place those angles at 135 degrees in quadrant 2 and 315 degrees in quadrant 4. The radian equivalents, as we can see, will be 3 pi over 4 and 7 pi over 4. The general solutions are going to be the ones that will be coterminal with these primary solutions. In degrees, we can write these out as 135 plus 360k, or 315 degrees plus 360k, where k is an integer. In radians, this will look like 3 pi over 4 plus 2 pi k, or 7 pi over 4 plus 2 pi k, where k is an integer. Now, the one thing I want to point out that is unique to solving equations involving the tangent function, not only are the general solutions going to be 360 degrees away from each other, But all of these angles are going to be 180 degrees apart from each other. So as we go around the circle, I'm 180 degrees apart to this one, 180 degrees apart to here, and then another 180, and another 180, and another 180, and so on. Since as we're going around the circle, we're hitting all these angles that are 180 degrees apart from each other, we could consolidate our solutions and write them as 135 degrees plus 180k, where k is an integer. Or in radians, we could say that the solutions include 3 pi over 4 radians plus pi k, where k is an integer. Both ways of writing out these solutions are correct. However, if WebAssign doesn't give you an option to list two solutions, it might be because it's asking you to consolidate these two solutions into one. Now let's look at where the reference angle isn't going to be one of our special mad-minute angles. Suppose the equation we're looking at is to solve the sine of x equals 0.6. The strategy is going to be exactly the same, but we're going to have to use our calculators to find the acute reference angle instead of just knowing what it is from our mad minutes experience. When we do that, we'll get the inverse sine of 0.6 is going to be 36.87 degrees or 0.6435 radians. Since we're interested where the sine of x is positive 0.6, possible solutions for that will be in quadrants 1 and 2. Now let's construct our reference triangles. Our graph will look like this. I've got two angles, one in quadrant 1, one in quadrant 2, that are each 36.87 degrees or 0.6435 radians away from the nearest x-axis. In quadrant 1, the angle measure will just be the reference angle, 36.87 degrees or 0.6435 radians. In quadrant 2, we'll take 180 degrees minus 36.87 degrees to get 143.13 degrees, or equivalently in radians, we could subtract 0.6435 from pi, which we can do by either using the pi button on our calculator or use the decimal equivalent 3.14159 to get 2.4981 radians. The general solutions, again, will be those coterminal with the primary solutions, which I'm showing again here. In degrees, the general solutions can be represented as 36.87 degrees plus 360k and 143.13 degrees plus 360k, where k is an integer. In radians, we're going to have the solutions as you see them here. Now, because this is a sine function, we can't consolidate the two sets of solutions into one very easily like we did with tangent. With tangent, the angles all had a common difference of 180 degrees. So when we consolidated the two general solutions, we could combine those arithmetic sequences together and simplify the expression further. With sine and cosine, we can't really do that because there isn't a common difference between the angle measures as I'm going around the circle. Here I've got, an obtuse angle. Here I've got a reflex angle. It's not consistent as I go around the circle. Why don't you try this one on your own? It's a very similar problem to the last one where you're finding first the primary solutions and then the general solutions to the equation tangent of x equals 2. It's going to be very much like the last one you did with tangent, except like the example on the previous slide, it's going to require the use of a calculator in order to get the correct reference angle. Since it will not be a 30, 45, or 60-degree angle, we're going to have something that won't look very pretty. Let's pause this video so you can try this one on your own. All right, the inverse tangent of 2 is going to get us 63.43 degrees or 1.1071 radians. As for the quadrants, we're going to have solutions in quadrants 1 and 3. We'll want to create reference triangles to locate these angles and to get their measures. The angles will look something like this, with terminal sides in quadrants 1 and 3, each 63.43 degrees away from the nearest x-axis. In quadrant 1, it's going to be just 63.43 degrees or 1.1071 radians. And in quadrant 3, we'll either add 180 degrees or pi radians to our reference angle to get 243.43 degrees or 4.2487 radians. Again, to get the general solutions, we just need to identify all the angles that are coterminal with these primary angles here. In degrees, we'll have 63.43 plus 360k, or 243.43 degrees plus 360k, where k is an integer. In radians, we'll have 1.1071 plus 2 pi k and 4.2487 plus 2 pi k, where k is an integer. Again, because all of these solutions are actually going to be 180 degrees or pi radians apart from each other, we can consolidate our solution set to say that x can equal 63.43 degrees plus 180k, where k is an integer, or 1.1071 radians plus pi k, where k is an integer. Again, this consolidation that we're doing here is a unique feature to just the tangent function. While there are ways we can consolidate solutions to the other problems into a single expression, in my opinion, it's not even worth looking at. Now that we've looked at the most basic of trigonometric equations, it's time to expand our horizons a bit. This equation is what we call quadratic type. And we call it that because I could make a substitution to say if y equaled the cosecant of x, then this equation becomes y squared minus 4 equals 0, which is a quadratic equation. Consequently, if we see something like this, what we'd like to try to do is factor it if we can, using our strategies for factoring that we learned back in previous algebra classes. One possible approach is to look at this and see that it looks like a difference of two perfect squares. You have cosecant squared x minus 4. 4 is 2 squared, cosecant squared is cosecant squared. So we could try to factor this, remembering in the back of our heads that if we have an expression in the form a squared minus b squared, we can factor that as a minus b times a plus b, which here would look like cosecant x minus 2 times cosecant x plus 2. And then we'll set that equal to 0. Remembering our rules from algebra, setting something like this with a product of two factors equal to 0 would mean that we can set each piece equal to 0 and solve them out separately, which will give us cosecant of x equals 2 and cosecant of x equals negative 2. Now, up until this point, all the examples we've used in this lesson have either been working with sine, cosine, or tangent. And those are nice because at worst, we have buttons to do those on our calculators. So we could apply reciprocal identities to flip this over, which will get you sine of x equals 1/2 or sine of x equals -1/2. Alternatively, if you didn't see the difference of squares pattern, you could start back in the beginning, add 4 to both sides of the equation to get cosecant squared of x equals 4. Then we could take the square root of both sides, which, as a reminder, we did talk about at the start of this video that would require we put in a plus or minus sign in front of the 2. So we have cosecant of x equals plus or minus 2. Taking the reciprocal gets you the sine of x equals plus or minus 1/2. So you're going to get the same answer whether you factored it as a difference of squares or whether I moved the 4 over and took the square root of both sides and put the plus or minus in. So what do we do from here? It's going to be the same approach that we did last time. We're going to take the inverse sine of 1/2, and we know the reference angle associated with that is 30 degrees or pi over 6 radians. Next, since we can have sine of x be positive 1/2 or sine of x be negative 1/2, we're going to have reference angle solutions in all 4 quadrants. In quadrants 1 and 2, the sine of x is going to be positive. And in quadrants 3 and 4, the sine of x is going to be negative. So we're going to have 4 primary solutions to this equation. In degrees, you're going to have 30 degrees, 150 degrees, 210 degrees, 330 degrees. In radians, you'll have pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 as your 4 primary solutions. Now, for time's sake, I'm not going to evaluate out the general solutions here, but if you had to, you could take each of the primary solutions and look for all of the angles coterminal with them. For degrees, we'd just add 360, and in radians, we would add 2 pi. Usually, the instructions to the problem will give you insight as to whether you want to find just the primary solutions or also the general solutions. If it says we want to find all solutions between 0 and 2 pi, like this one does here, you just want the primary solutions. If it says find all solutions or to find the real solutions or to find the solutions between negative infinity and positive infinity, that's when you want the general solutions. Let's try another one that will fit the quadratic type. Here we want to solve the equation 2 sine squared x plus 7 sine x equals 4. This time, we are only interested in the primary solutions of the equation, and our giveaway with that is noticing this symbolism. It says x, it has the bent out e, and then an interval notation 0 to 2 pi. It says that the values of x I'm interested in need to be greater than or equal to 0 and less than 2 pi. So primary solutions between 0 and 2 pi, only one revolution of the full circle. When it's presented like this, it's like saying I want to solve the equation 2y squared plus 7y equals 4. When we have problems like this, remember from your algebra days, you always want to set this equal to 0 first, which will end up looking like 2y squared plus 7y minus 4 equals 0. From here, we want to try to factor this expression the best way that we can. We can either use the AC method, or if you have some of the programs that I gave you to install on your calculator, you could use trifact or quadrat to come up with solutions for these. Factoring this expression is going to give you 2y minus 1 times y plus 4 equals 0. Essentially, if I think of y as being a placeholder for the sine of x, this equation, 2 sine squared x plus 7 sine x minus 4 equals 0, should factor as 2 sine x minus 1 times sine x plus 4 equals 0. From here, we want to set each piece equal to 0 and isolate the sign of x. In the first factor, if you add 1 and divide by 2, you get sine of x equals 1/2. In the second factor, you subtract 4 from both sides to get sine of x equals -4. Now, in this second equation, I'm hoping that you'll see that right away, this is going to cause us some problems because the inverse sine of -4 doesn't exist. The domain of the inverse sine function consists of only numbers between -1 and +1. So you cannot construct a reference triangle that is going to have a sine ratio bigger than 1 or less than -1. To do so would mean that you had an opposite side on your reference triangle that is 4 times larger than your hypotenuse, which can't happen. Consequently, we're going to cross off that factor as being extraneous, and we will focus exclusively on the factors that is generated on the left, the sine of x equals 1/2. We've already looked at this one before, so you might be able to do this one in your head already. The inverse sine of 1/2 is 30 degrees or pi/6 radians. We're going to have solutions in quadrants 1 and 2 because that's where the sine function is positive. We construct our reference triangles and see that the angles are going to be 30 degrees in quadrant 1 or 30 degrees in quadrant 2, meaning that their measures will be 30 degrees or 150 degrees, or their radian equivalents, pi/6 and 5 pi/6. Why don't you try this one on your own? Solve the equation 2 cosine squared x plus 3 cosine of x plus 1 equals 0. You want solutions between 0 and 2 pi, so I'm only interested in the primary solutions, not the general solutions. Pause this video and see what you can do with this one on your own. You might be able to recognize the factoring pattern on this one right away. But if you don't, we can make this substitution where y equals sine of x, similar to what we did on the previous example, and get this to look like a more familiar quadratic equation, 2y squared plus 3y plus 1 equals 0. That's going to factor as 2y plus 1 times y plus 1 equals 0. Following that same pattern means that when I have 2 cosine squared x plus 3 cosine x plus 1 equals 0, that must factor as 2 cosine x plus 1 times cosine x plus 1. Now you want to set each piece equal to 0 and solve for x. In the first factor, we subtract 1 and divide by 2 to get cosine of x equals -1/2. In the second factor, you just subtract 1 from both sides to get cosine of x equals -1. We see we want the cosine of x to be negative in both of these equations, and we know that the cosine of x is negative in quadrants 2 and 3. From here, let's look at each equation separately. The inverse cosine of 1/2 is 60 degrees or pi/3. The inverse cosine of 1 is 0. Now I need to consider what those reference triangles actually look like in quadrants 2 and 3. Here's my graph for this. Let's start with the 60-degree reference angles. In quadrant 2, 60 degrees above the negative x-axis places us at 120 degrees, while 60 degrees below the x-axis in quadrant 3 will be 240 degrees. Now we have to think for a second about what's happening in the second factor. To say that we're going 0 degrees above or below the negative x-axis means we're stuck at 180 degrees. Now, another approach we could take to this is just taking the inverse cosine of -1, which is going to give you just 180 degrees or pi radians, which again confirms what we should be seeing here on our graph. Either strategy is going to be working well for you in this problem. When writing up your solutions, you want to consolidate these into a single set of braces and put the values in increasing order. So we'd write them as 120 degrees, 180 degrees, or 240 degrees. However, since we were asked to put our final solutions in radians, we really should be writing it as 2 pi over 3, pi, and 4 pi over 3 as our three primary solutions to this equation. All right, I've got 6 more slides here, and the examples I'm going to show you now are more like the ones you would see in section 7.5. While I could just create a separate video for section 7.5, I figured that I'm on a roll. And second, that's one less video that I need to create and edit. Third, that's one less video you need to watch. So let's go through these 6 slides, and then you'll be all covered on all the material you're going to need for both section 7.4 and 7.5. This one's a little different because we're going to be messing with the angle's frequency, or where the b value, when we're looking at the graph of this, doesn't equal 1. Suppose I have, solving the equation, sine of 2x equals 1/2, and I'm looking for just the primary solutions for this one to make it simpler. Now, what you do not need to do is dive into the double angle formula to try to figure this one out. But knowing we have a double angle here is going to mean that we're not going to be able to solve it as easily as some of the other problems we've looked at so far in this presentation. Our first step is to substitute theta for 2x and try to solve it like it was one from earlier in this lesson. So if we had written it as the sine of theta equals 1/2, we've done this problem already a few times. We would first take the inverse sine of 1/2, which will get you 30 degrees or pi over 6 radians. As for the quadrants, the sine of theta is positive in quadrants 1 and 2. So if I were looking for the reference angle solutions for theta, we'd have 30 degrees or pi over 6 radians in quadrant 1. Or we would have 150 degrees or 5 pi over 6 radians in quadrant 2. Here is where things get different. Our second step is going to be to change the range for your solutions based on the b value, which for this problem is going to be 2, since I'm taking the sine of 2x. Let's look at the logic here. We just solved for two angles for theta between 0 and 360 such that the sine of theta equals 1/2. The problem is that this was not the question that was asked. I didn't ask you to find angle theta. I asked you to find the measures of all angles x between 0 and 360 degrees, or 0 and 2 pi radians, such that the sine of 2x equals 1/2. So if I want all of my angles to be between 0 and 2 pi, but the value I had for theta is going to be the same as 2x, then in reality, what I'm going to need to look for are all the answers for x, or rather for 2x, which are really your answers for theta, to be between 0 and 4 pi. Well, why 0 to 4 pi? I'm going to divide all of those answers by 2 to get my answers for x. x. So ultimately what this means here is I need to go around my unit circle twice because of the b equals 2 to find an extra set of coterminal solutions to this equation, which will ultimately fall between 0 and 2 pi. But once I divide everything by 2, the results are all going to fall back between 0 and 2 pi. Let's see what this looks like in action. I said the first two primary solutions were going to be pi over 6 and 5 pi over 6. If I go around the unit circle a second time, so I'm traveling from 0 to 4 pi radians, I'm going to run into the angles 13 pi over 6 and 17 pi over 6. These are both coterminal with the first two angles that when I take the sine of those angles, the sine of 13 pi over 6, the sine of 17 pi over 6 will equal 1/2. From here, we'll divide all of those answers by 2, which will give us pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. The degree equivalents for those, which I don't have room to show here, are going to be 15 degrees, 75 degrees, 195 degrees, and 255 degrees. Those four angles are all angles between 0 and 360 degrees, or with the ones that are shown here, between 0 and 2 pi radians, such that when I double these angle measures, the sine of the doubled angles here will equal 1/2. This might make more sense if I look at this in a graphing utility like Desmos. So here is the graph of my equation y equals sine of x. And let's go ahead and insert the horizontal line y equals 1/2. And I'll make it a dash line so we can see that it's going to be different. I can see here that there are going to be intersection points at pi over 6 comma 1/2, 5 pi over 6 comma 1/2, and that those are the two places between 0 and 2 pi where the sine of x will equal 1/2. Now let's change the graph up a bit to actually look at the sine of 2x equals 1/2. If I look at the sine of x equals 1/2 and I look at the horizontal line very carefully, you're going to see that it's going to intersect the sine wave in 4 different places. That's because I'm able to squeeze in 2 full cycles of the sine wave between 0 and 2 pi radians. And so that makes these 4 solutions here where I would have had only 2. So the strategy that we're going to do is treat this as the sine of 1x, and then I'm going to go around this circle twice to find the 4 locations between 0 and 4 pi that will equal 1/2. But then since I'm dividing by 2, that's now going to give me 4 angles between 0 and 2 pi, such that when I double these values, the sine of the doubled angle will equal 1/2. Hopefully that puts things into a good perspective here for you. Here's a similar problem. Here I've got the tangent of 3x equals 1. And I'm looking for the primary solutions for this equation as well. The process is going to be very similar to what I just did in the last example, where I'm going to substitute in theta for 3x so we can treat this as though we were solving the equation tangent of theta equals 1. The inverse tangent of 1 is 45 degrees, or pi over 4 radians. We also know that the tangent function is going to be positive in quadrants 1 and 3. So if we were to place those angles in quadrant 1, we would have 45 degrees, and in quadrant 3, we're going to have 225 degrees. The radian equivalents of those would be pi over 4 and 5 pi over 4. Now let's look at the impact of that 3 in front of the x. What we just solved for was theta, but what we want are all the values of x between 0 and 2 pi that solve this equation out. What we have is theta, and theta is the same as 3x. So if I want all angles for x to be between 0 and 2 pi, I'm going to need my angles for 3x to be between 0 and 6 pi. In essence, I want to go around the circle 3 times and look for all solutions that will fall between 0 and 6 pi, so that after we divide by 3, everything we're left with will be solutions between 0 and 2 pi. So now let's go around the circle looking for those coterminal angles. Here, if I was to just keep adding pi radians to each successive, or 2 pi radians to each of those primary solutions, we're going to get these 6 answers. Pi over 4, 5 pi over 4, 9 pi over 4, 13 pi over 4, 17 pi over 4, 21 pi over 4. The tangent of all of these 6 angles equals 1. Now what I want to do is divide each of those answers by 3, because those are my answers for 3x. When we divide those answers by 3, we're going to get pi over 12, 5 pi over 12, 9 pi over 12, 13 pi over 12, 17 pi over 12, and 21 pi over 12. Those 6 angles here in the final set of braces are all going to be angles that fall between 0 and 2 pi, such that when I triple those angles, the tangent of the tripled angle equals 1. Summing up, normally we're going to have 2 solutions to most of these problems. When we use the 2x in the last example, we went around the circle twice, we ended up with 4 solutions. With this example, the angle being 3x, it created 6 solutions. If I went all the way to 4x, we would create 8 solutions. So this b value, the coefficient in front of the x, the frequency, essentially is going to multiply potentially the number of solutions that we need by our standard one, which would be 2. So what if we went to a half x? Well, based on this pattern we were just looking at, what we would expect to have here is half the number of solutions, which is just going to be 1 solution. So the cosine of a half x equals the negative square root of 2 over 2. If I substitute in theta for x and start by taking the inverse cosine of the square root of 2 over 2, we get 45 degrees, or pi over 4 radians. We also know that the cosine of theta will be negative in quadrants 2 and 3. So the possible solutions are going to normally be either 135 degrees in quadrant 2 or 225 degrees in quadrant 3. When we're looking at our range here, we know we want x to be between 0 and 2 pi. But theta is defined as being equal to a half an x. That means I want to look only for angles between 0 and pi. Because in order to solve for x, we know we're going to have to double our answers. Now, if you're not comfortable with this, let's walk it through. We want to only go around the circle half a revolution because after we multiply by 2, we're going to end up with solutions between 0 and 2 pi. If we didn't restrict this, if we had just said theta, or 1/2 x, equals 3 pi over 4 and 5 pi over 4 as our primary solutions, and we doubled those results, what we'd end up with is 3 pi over 2 and 5 pi over 2. If our values for x have to be between 0 and 2 pi, then 5 pi over 2 is going to be too big. So our final answers is going to just be x equals 3 pi over 2. The last type of equations we want to approach are ones where we're going to be using some of the trigonometric identities covered in section 7.1, 7.2, and 7.3 to rearrange the equation before we can hope to solve for x. Here is one such example. Suppose we want to solve the equation cosine 2x times sine of x plus sine of x equals 0. And we want to look for just primary solutions between 0 and 2 pi. None of our other examples up to this point mixed and matched different trig functions like this one with sines and cosines in the same problem. Additionally, this one also has the distinction that it has a double angle in it, and it's really hard to solve problems if we can't isolate that double angle or use one of the double angle identities to reduce this down. The thing I see in this equation, though, is that there is a sine of x in each term on the left-hand side of the equal sign. So perhaps we should be thinking about taking out a common factor of the sine of x and then set each piece equal to 0. This will give us the sine of x times the cosine of 2x plus 1 equals 0. Let's look at the sine of x equals 0 piece first. The inverse sine of 0 is 0. And from our quadrantal angles experience, we should remember that the sine of x equals 0 at 0 degrees or 180 degrees. So that takes care of that factor. Now, with the other side, we've got cosine of 2x plus 1 equals 0. To solve this, we can move the 1 to the other side and try to solve it out like the ones we did before when we had double angles. I'll make a substitution, theta equals 2x, to rewrite this equation as cosine of theta equals -1. And we know that the cosine of theta will be -1 when theta equals 180 degrees or pi radians. We also should remember that since I want angles for x to be between 0 and 2 pi, and what I have is 2x, then I need to go around the circle twice to find all of the best solutions. And then this way, theta, or 2x, will be 180 degrees or 540 degrees, which when I divide them in half will get you 90 degrees or 270 degrees. Finally, you want to consolidate your answers from both parts of this equation in order to get a single solution set. So you'll have x equals 0, 90, 180, or 270 degrees. But of course, they want our final answer in radians, which would be 0, pi over 2, pi, and 3 pi over 2. This one has both a quadratic component in it and a double angle component in it. Solve the equation cosine squared x plus cosine 2x equals -1 for angles x between 0 and 2 pi. This is not a case where you're going to be able to factor a cosine out of all of this because the angles you're working with are different. In the first term, you've got the angles x. In the second term, the angle is 2x. So what you're going to need to do is use a double angle identity to reduce the cosine of 2x into something where the angle is 1x instead of 2x. So here's my equation. Cosine squared x plus cosine 2x equals -1. If you recall, there are three different double angle identity formulas available for the cosine of 2x. Given the choices, I want to use the one that says cosine of 2x equals 2 cosine squared x minus 1. I want to use this formula because it will allow everything to be converted into cosines, and because any other variation on this formula is going to introduce sines, and that will get very messy very quickly. Now that everything is in cosines, let's combine our like terms and get 3 cosine squared of x minus 1 equals 1. Adding 1 to the other side will get this to become 3 cosine squared x equals 0, which is just going to simplify as the cosine squared of x equals 0, or taking the square root, cosine of x equals 0. Remembering our options with quadrantal angles, your answers for x are going to be either 90 degrees or 270 degrees, which in radians will convert to pi over 2 or 3 pi over 2. Now, it's possible you could also say that this is a 90-degree reference angle in quadrant 1 or quadrant 4 and get the same results. But anyway, this is going to be your final answer. We have two angles that will satisfy this initial equation, cosine squared x plus cosine 2x equals -1, where these two angles are both between 0 and 2 pi. Okay, last example. Here we have the equation 2 cosine x minus 3 tangent x equals 0. This one has its own unique challenges because you're mixing two different trig functions in the same problem. There isn't a common factor, there isn't a square or a double angle we can work with. The one thing we can try is to use reciprocal identities to turn everything into sines and cosines. That is going to make this turn into 2 cosine x minus 3 times the sine of x over the cosine of x equals 0. Next, let's multiply through by the common denominator of cosine of x and see what happens. That's going to give us 2 cosine squared of x minus 3 sine x equals 0. Now you're wondering what we can do with this because we still have a sine mixed in with a cosine in the same equation. However, what I also see is that there's this cosine squared x in here, which if we use a Pythagorean identity, we can convert that into something with just sines in it. Since sine squared plus cosine squared equals 1, I can rewrite the cosine squared x as 1 minus sine squared x and substitute that in to the expression, which will leave us with 2 times 1 minus sine squared x minus 3 sine x equals 0. Now it looks like we might be getting somewhere. Let's distribute the 2, and that's going to give us the equation 2 minus 2 sine squared x minus 3 sine x equals 0. This looks to me like it's going to fall into the category of a quadratic type that we looked at earlier in this video. So let's rearrange this so it looks something that will be easier to factor, putting the sine squared term out in front and make the sine squared term positive. Doing that is going to make this equation become positive 2 sine squared x plus 3 sine x minus 2 equals 0. Now that it's in this form, let's try to factor this like a quadratic and set each piece equal to 0. Now, if you don't see the factoring strategy here, You may want to do a substitution like we did in an earlier example to make this look like 2y squared plus 3y minus 2 equals 0. Next, we'll apply either trifact or the AC method to try to break this down. That's going to get you 2 sine x minus 1 times sine of x plus 2 equals 0. We'll set each piece equal to 0 and try to solve for the sine of x. We should get sine of x equals 1/2 or sine of x equals -2. Now, sine of x, we've said, can never be bigger than 1 or less than -1, which means that the second piece isn't going to generate any real answers. In the end, we're left with just sine of x equals 1/2, which we've done many times before. So our final answers here are going to be 30 degrees or 150 degrees. But since we want this to be in radians, we'll have final answers of pi over 6 and 5 pi over 6 radians. Congratulations! You have made it to the end of another double lecture video without your brain hopefully turning into mush. The plus side with this one is that this is the only lecture video that you're going to be watching this week. So once you've gotten through this one, you get a little break before we head into things next week. Usually, when I've set up a double lecture video, we were doing 2 assignments in one day and then a third assignment for the end of the week. That is not the case here. We only have 2 assignments that we're going to be covering this week that are section 7.4 and 7.5, and you have the material that you need for both sections within this one video. Again, you might have asked, couldn't you have split this in 2? Well, the reality is that while we've already had the first 18 slides, we're going to cover section 7.4, it made more sense to just add 6 more slides to get section 7.5 and get it over and done with in the same video. Anyway, here are the problem challenge problems for section 7.4 and 7.5. We're going to be talking about these at a couple of upcoming ORT sessions, so as always, it is best if you can look at these ahead of time so you know what questions to ask. As always, if you have any questions or worries about these problems, feel free to contact me via email or post your question on the discussion board. Thanks for watching, and we'll see you all soon.